Every time you look at the stars, you're looking into the past, and this video is about 20 times that ancient light changed what we know. It gives you a new view of the whole history of the cosmos. From how it started to how it might end, there was a faint hiss from empty space. It proved the universe had a beginning, and there was a dying star that dimmed. It showed a force that could tear everything apart. So the question is, what's the most important message the universe has sent? The first big moment didn't come from a telescope. It came from a room full of people and a clash of ideas. This was in 1920. Two astronomers, Harlow Shapley and Heber Curtis, they stood there with all the best observations anyone had. Shapley was convinced. He thought the Milky Way was everything, the whole universe, just this one vast island of stars. But Curtis, he looked at the same data. He looked at those fuzzy spirals in the sky, and he thought they were something else, separate islands, entire other universes far beyond our own. The whole debate turned on nova. These sudden explosions of stars inside those spirals, they looked so faint. That faintness suggested incredible distances. Distances so huge, they could knock our galaxy right out of the center of everything. But it was still just a theory, a good argument waiting for proof. Then the proof came just a few years later. It came on light that was over 2 million years old. Edwin Hubble used the new Hooker telescope, the giant one. He pointed it at the great spiral in Andromeda, and inside it he found a certain kind of star. A Cepheid variable. This star pulses, its light goes bright and dim in a rhythm, and that rhythm is a yardstick. By seeing how bright it looked to us, he could work out its real distance. The number was clear and it was colossal. Andromeda wasn't some cloud inside our galaxy. It was a galaxy itself. A whole city of stars, so far away its light was an ancient message. Just like that, the universe got bigger. We weren't the only island anymore. We were just one shore, in an archipelago that went on farther than you could imagine. Our place in the cosmos was rewritten, and then, as they started to map this new archipelago, astronomers saw something strange in the light from these distant islands. A faint red stain, a clue that would lead to something even bigger than finding the galaxies. That red stain in the light was a message. Edwin Hubble figured out how to read it. He'd take light from these distant galaxies and split it into a rainbow, into spectra, and in those rainbows you see dark lines like a barcode. That barcode tells you what elements are in that star. But the barcodes from these galaxies, they were all wrong. Every line was shifted toward the red. That's the redshift, and it meant one thing. Those galaxies were moving away from us. It's the same as a train whistle dropping in pitch as it moves away from you, but written in light, across millions of light years. The universe was stretching the light inside it, making it redder. That was shocking, but then came the real revelation. Hubble and Milton Humason, they measured the distances. They paired a galaxy's redshift with how far away it was, and they found this direct relationship, simple and terrifying. The farther away the galaxy, the greater its redshift. The faster it was fleeing. It wasn't just that everything was moving away from us. Space itself, the fabric of the cosmos, was expanding. The more space between 2 points, the faster that stretch carried them apart. That was Hubble's law, and it changed everything. A static, eternal universe was gone. Now you had a cosmos with a history, a story with a first chapter. If everything is flying apart now, then you rewind the film. Everything was close together in the past. Rewind it all the way, and you're forced to imagine a moment. Unimaginable density, unimaginable heat, a beginning. That ancient, reddened light from the galaxies that was the first observable clue to the Big Bang. It told us the universe had a birthday, And if the universe had a beginning, then the next question was haunting. Could we ever see it? Could we find light from that first fiery moment? That first flash was hidden. There was a wall of plasma, a hot, dense fog. For hundreds of thousands of years, the universe was this glowing soup. It was so thick light couldn't travel. It was trapped, bouncing around. Then the universe expanded. It cooled enough for atoms to form, and the fog lifted. That first light, after being trapped, shot out in every direction. That flash has been traveling ever since, for over 13 billion years, and in 1965, two radio astronomers, Arno Penzias and Robert Wilson, they picked up its echo by accident. They were using a giant horn-shaped antenna, listening for faint signals from space, but there was this hiss, a persistent, annoying hiss. It came from every direction. They checked everything. They even cleaned out pigeon droppings from the antenna, thinking that was it, but the hiss stayed. It was a uniform whisper. A faint microwave signal bathing the whole sky, just a few degrees above absolute zero. This wasn't a flaw in their equipment. This was the universe itself speaking. They'd found the cosmic microwave background. That hiss was the cooled remnant of that first flash. The moment the cosmos became transparent, think of a blacksmith pulling white-hot iron from a forge. It glows brilliant white, then as it cools it turns orange, then a dull red. Finally, it's a cold, dark piece of metal, but it still radiates a tiny bit of heat if you hold your hand close. The universe did that. That initial brilliant flash has been traveling and stretching with the expansion of space. Its waves have stretched from visible light all the way down to microwaves. It's cooled to 2.7 degrees above absolute zero, but it's everywhere. You point a sensitive radio telescope anywhere, you hear that ancient whisper. This was the smoking gun, the proof the universe began in a hot, dense state. The Big Bang Theory wasn't just an idea anymore, it was the foundation. But the story didn't end there. Satellites like the Cosmic Background Explorer and later Planck, they mapped this whisper with incredible precision. They found it was almost perfectly uniform, the same temperature everywhere, almost. There were tiny variations, ripples, fluctuations of 1 part in 100,000. These tiny imperfections in the ancient glow were the seeds, slightly denser patches of that early plasma, shown as slightly warmer spots in the microwave sky. Gravity worked on those seeds for billions of years. They became the first stars, the first galaxies, the great clusters we see now. That faint hiss is a treasure map. It tells us the age of the universe, its composition, even the shape of space-time. It's our most direct link to the universe's infancy, a baby picture taken when the cosmos was 380,000 years old. And it started with two astronomers trying to get rid of a noise. This ancient whisper told us how the universe began, but to understand its fate, we needed a different light. Not a uniform glow, the brilliant, violent flash of a star's death. That baby picture from the cosmic microwave background gave us a starting point, but the story of the universe isn't just about where it began. It's about where it's going, what's its ultimate fate. For most of the 20th century, cosmologists thought they knew. They had the Big Bang, they had the expansion. And they had gravity. Gravity pulls everything together, so the logical conclusion was that the expansion had to be slowing down. The only question was how much. Would it slow to a gentle halt, or would it reverse, pull everything back into a fiery crunch? To find out, you needed to measure the expansion rate. Not just now, but in the distant past, you needed a time machine, and in the late 1990s, two teams of astronomers found one. Their time machine was a particular kind of stellar catastrophe. A Type 1, a supernova. This happens in a binary star system. A dense white dwarf star siphons material from its companion. It pulls matter onto itself until it reaches a critical mass. A precise, catastrophic tipping point. then it explodes. This explosion is so violent, so perfectly tuned, that every single one shines with nearly the same peak brightness. They're cosmic standard candles. If you know how bright something truly is, and you see how dim it looks from here, you can calculate exactly how far away it is. These supernovae are the most reliable mile markers in the cosmos. The two teams, one led by Saul Perlmutter and another by Brian Schmidt and Adam Rees, set out on a monumental hunt. They pointed the world's most powerful telescopes at the deepest reaches of space. They were looking for the faint, ancient light of supernova that exploded when the universe was half its current age. They measured their distances, and then they measured something else, the redshift of their host galaxies. This told them how much the universe had stretched since the light left that dying star. By comparing distance to redshift, they could see how the expansion rate had changed over billions of years. The result was not just surprising, it was universe-shattering. The most distant supernova, the oldest ones, were fainter than they should have been. They were farther away than anyone's models predicted. The only way to explain it was if the expansion of the universe was not slowing down. It was speeding up. Something was fighting against gravity's relentless pull and winning. They called that something dark energy, a mysterious pressure inherent to the fabric of space itself, pushing galaxies apart. The light from those ancient stellar explosions rewrote our cosmic destiny. It revealed that roughly 68% of everything in the universe is this enigmatic force we cannot see and do not understand. The universe isn't just expanding, it's accelerating into a future of increasing isolation and darkness. This discovery, built on the precise flash of dying stars, showed that the greatest chapters of our cosmic story are still being written by forces we have only just begun to name. And if we wanted to map this strange new cosmos, we would need to find a way to see the invisible. Dark energy showed us how the universe would end, but it left something else unanswered. What is the cosmos built from? To find out, we had to find a way to see what we couldn't see. And in 1979, the universe gave us a kind of lens. Astronomers were looking at a very bright, distant quasar. That's the core of a young galaxy lit up by a huge black hole. This one was called Q0957+561, but the data was strange. It showed two quasars, not one. They were exact copies, same light, same color, same distance. The odds of two real objects being that perfectly aligned were zero, so it had to be an illusion. A massive cluster of galaxies was right between us and that one real quasar. Einstein's theory says mass bends space and time. A heavy object doesn't just pull on things. It bends the path of light itself. This cluster worked like a lens. It warped space-time and split the quasar's single beam of light. It made that ancient light take two separate routes around the cluster's gravity, which gave us two images. This was the first strong gravitational lens we found. They named it the twin quasar, and it proved the universe could magnify and twist light from its farthest edges. We call these warped shapes Einstein rings or arcs. They're how nature shows us the hidden framework of everything, because the key is this. How much the light bends depends on the total mass of the thing doing the lensing. When they calculated the mass of that galaxy cluster, the numbers didn't add up. The stars and gas you could see didn't have enough gravity to bend the light that much. There was extra mass there bending the light, mass we couldn't see. This became one of the clearest signs of dark matter, that invisible stuff that makes up about 27% of the universe. Gravitational lensing made the cosmos itself an observatory. By looking at these rings and arcs, we can chart where dark matter is. We can see its faint halo around galaxies. We can see it forming the cosmic web, and lensing also works as a natural telescope. It can magnify galaxies so far away we'd never see them otherwise. It lets us look at the first stars. On a smaller scale, it can even find lone planets drifting between stars. by the tiny flash they make when their gravity briefly focuses the light of a star behind them. Every warped image, every Einstein ring is a signal. It tells us space isn't a fixed backdrop. It's a flexible fabric shaped by the mass inside it. That light from the twin quasar, traveling for billions of years, did more than show us a distant object. It showed us the hidden structure of reality. It gave us a tool to weigh what we can't see, and if we could map the dark matter holding galaxies together, then the next question was right there. What were those galaxies and everything in them really made of? Newton's rainbow was just the start. When scientists in the 19th century pointed their prisms at starlight, they saw something else. The rainbow was still there, but it was crossed by these dark lines. Like a barcode printed across the colors, each line was a missing color, a specific wavelength of light that something had absorbed, and every element in the universe absorbs its own unique set of wavelengths. So these dark lines were a fingerprint, a signature written in the light itself. This technique, spectroscopy, became a kind of translator. You could point a telescope at a star, capture its ancient light, spread that light into a spectrum, and read what it was made of from millions of light years away. The message was simple and profound. The same dark lines kept appearing, the fingerprint of hydrogen, which is everywhere, the signature of helium, the marks of carbon, oxygen, iron, silicon. Every element we knew here on Earth was out there, woven into stars and nebulae. That ancient light told us two big things. First, it showed us the universal recipe. The cosmos is made from the same ingredients everywhere. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged somewhere else a long time ago and delivered across space. We are, as Carl Sagan said, made of star stuff. Second, those spectral lines showed us the process. They revealed that stars are nuclear furnaces. In their cores, under immense pressure and heat, atoms fuse together. Hydrogen fuses into helium, then helium into carbon and oxygen. In the biggest stars, that fusion chain goes all the way to iron. The specific energies from these reactions imprint themselves on the star's light, leaving those telltale dark lines in its outer layers. Spectroscopy let us watch this alchemy from across the galaxy, but the story gets bigger. When we point our spectroscopes at the most distant things like quasars, the light doesn't just carry the quasar's own fingerprint. On its billion-year journey to us, that light passes through clouds of gas in the vast emptiness between galaxies, and atoms in those clouds absorb their specific colors too. So the quasar's spectrum becomes a probe. It's like shining a bright flashlight through a fog. By seeing which colors are missing from the beam when it gets here, we can map the fog itself. That's how we found and measured the intergalactic medium, the incredibly thin soup of gas that fills the space between galaxies. Its composition, its temperature, how it's spread out. All of it read from the shadows written in ancient light. It showed us that even the great voids aren't completely empty. They're laced with primordial elements, the raw material for future galaxies. So that simple act of passing light through a prism unlocked the chemistry of the cosmos. It connected us directly to the life cycle of stars. Every element heavier than hydrogen and helium was cooked in a stellar core or forged in the violent death of a supernova, then scattered into space to eventually become part of new stars, new planets, and us. The light is a chronicle, a family history written in atomic signatures, and if light could carry that kind of detailed chemical message, maybe it could carry another kind of message, something even more fundamental about the very fabric of reality it traveled through. That chemical map in the light was one story, but the universe sends another kind of message, a steady pulse. In 1967, Jocelyn Bell Burnell was looking at data from a radio telescope she built. She saw this repeating signal. It wasn't static, it wasn't interference, it was a sharp beep from deep space every 1.33 seconds, so regular it seemed artificial. Her team called it LGM, Little Green Men. Maybe it was aliens. The truth was almost stranger. It wasn't an alien beacon. It was a star's death cry turned into a perfect clock. They found the first pulsar. A pulsar is what's left after a huge star explodes. The core collapses. It becomes a neutron star, a city's mass crushed into a mountain size. A teaspoon would weigh billions of tons, and it spins. Its magnetic field acts like a lighthouse. Beams shoot out from the poles. If those beams sweep past Earth, we see a flash. A pulse every rotation. The precision is breathtaking. These things spin hundreds of times a second. Their rhythm is more stable than our best atomic clocks. That stability, carried on radio waves, makes them perfect tools for testing physics. They became labs for Einstein's relativity. The famous test was in 1974. The Hulse-Taylor binary, two neutron stars orbiting each other every few hours. Einstein said a system like that should lose energy. It should radiate gravitational waves. Ripples in spacetime, losing energy, the stars should spiral inward. Their orbit should decay by a predictable bit. For decades, astronomers timed the pulses from one pulsar. They tracked the exact arrival of its flashes, and they found it. The orbit was shrinking. The stars were spiraling together at exactly the rate Einstein predicted. That clockwork light gave the first real evidence for gravitational waves, a theoretical triumph seen in the timing of a stellar corpse. Now we listen for gravitational waves directly with LIGO. But pulsars are part of a bigger hunt. Pulsar timing arrays, networks of these cosmic clocks across the galaxy. By watching dozens of pulsars for years, scientists look for tiny hiccups in their timing. Correlated hiccups, those could be from low-frequency gravitational waves, the rumble from supermassive black holes merging in distant galaxies. We're using dead stars as a galaxy-sized detector. Listening for the deepest hum, so those rhythmic flashes aren't just a curiosity. They show the most extreme matter in the universe, and they're a precision instrument. A gift from stellar graves, letting us probe the subtle warp of spacetime itself. But to understand how such a thing is born, you have to see the violence of its creation. Neutron stars have their rhythm, their pulse, but there's another kind of stellar death, a final scream, one so loud it can outshine a whole galaxy. Back in the late 60s, the U.S. had military satellites orbiting Earth, watching. Their job was to look for the flash of gamma rays, a sign of a secret nuclear test in space. They found flashes. But they weren't coming from Earth. They were coming from deep space, brief, intense bursts of the highest energy light, random, unpredictable, lasting from milliseconds to a few minutes, then vanishing. Gone, that data was classified for years. When it finally came out, astronomers had no idea what could produce that much energy and then just disappear. Gamma-ray bursts became this deep mystery. For 30 years, theories swirled. Were they inside our own galaxy, maybe neutron stars colliding, or were they from the far edges of the universe? The problem was they were so brief. By the time you got an alert, the flash was over. Nothing left to point a telescope at. Then, in 1997, the breakthrough. An Italian-Dutch satellite called Beppo-SAX. It had this crucial ability. It could quickly locate the X-ray afterglow that lingers right after the gamma-ray flash. For the first time, ground telescopes got coordinates fast enough. They swiveled and they saw it, a faint, fading pinpoint of visible light in a distant galaxy. That light was the key. They analyzed its spectrum, measured the redshift. The number was enormous. This burst and others after it weren't in our backyard. They were billions of light years away. To appear that bright from such a distance meant the energy was almost incomprehensible. In a few seconds, a single gamma-ray burst can release more energy than our sun will in its entire 10 billion-year life. It's the most powerful explosion since the Big Bang. So what creates it? The afterglow tells that story too. There seem to be two main culprits. The long bursts over 2 seconds, they're thought to be the birth cries of black holes. They come from hypernova, the catastrophic collapse of a massive, rapidly spinning star. Its core collapses into a black hole, and jets of material blast outward at nearly light speed. If one of those jets is pointed right at Earth, we see the fireworks, a gamma-ray burst. The shorter bursts under 2 seconds, they're thought to be the final embrace. Two neutron stars, or a neutron star and a black hole, spiraling together and merging. That also creates a black hole, blasts out jets. This light is more than a spectacle. It's a tool. That brilliant flash travels for billions of years across the expanding universe. It passes through everything in its path: clouds of gas, the halos of galaxies, the vast filaments of the cosmic web. Atoms in those clouds absorb specific wavelengths. They leave their fingerprints on the burst's light. So by reading the afterglow spectrum, we get a core sample of the universe. A probe, it illuminates the conditions and the composition of the cosmos across immense distances. Back to a time when the universe was young, these bursts are cosmic lighthouses. Shining through the fog of time, they show us the most violent creative forces at work. The death of a star so colossal it gives birth to a new black hole, seeding the universe with heavy elements forged in its own destruction. It's a reminder. The cosmos writes its history not just in the gentle glow of starlight, but in brilliant, catastrophic strokes. And while these bursts illuminate the farthest frontiers, a different kind of light has been mapping the architecture of our own galactic neighborhood. Patiently, for centuries, the brilliant flash of a gamma-ray burst, it's a beacon from the cosmic frontier. But for a sense of home, you have to look inward. To map our own city of stars, the Milky Way, from inside it, and that was a profound challenge. For centuries, the view was blocked by something simple. Just billions of tiny grains, carbon and silicon, floating between the stars. They scatter visible light, they absorb it, they create a veil across the galactic plane. It was like living in a dense fog, trying to draw a map of a continent by sight alone. The first key to piercing that veil wasn't a new kind of light. It was a new kind of clock, a star that beats like a heart. Henrietta Leavitt, in the early 20th century, was studying variable stars. She noticed a pattern in a class called Cepheid variables. These stars pulsate, they grow brighter and dimmer in a regular rhythm, and she found the longer the period of that rhythm, the greater the star's true brightness. It was a cosmic yardstick. Time the heartbeat, and you know how bright the star truly is. Compare that to how faint it looks from Earth, and you can calculate its distance. With precision, this tool went to Harlow Shapley. He used Cepheids inside globular clusters, those dense, ancient swarms of stars that orbit the galactic core. By measuring distances to these clusters, he could trace their three-dimensional distribution, and they weren't centered on our sun. They formed a great spherical halo. Around a point tens of thousands of light years away toward Sagittarius, the message in that Cepheid light was clear and humbling. Our sun was not the center. We lived in the galactic suburbs. The true heart of the Milky Way was far away, hidden behind that curtain of dust. But to see that heart, to trace the spiral arms we suspected were there, we needed light that could slip through the fog. That light was infrared. Dust that blocks visible light glows with its own heat. It radiates in the infrared, and longer infrared wavelengths can pass through dust clouds. Relatively unscathed, it's the difference between a flashlight in thick fog and a heat sensor. The heat sensor sees through. This revolution started with ground-based telescopes. Then it soared with space observatories, like the Spitzer Space Telescope. Freed from Earth's atmosphere, Spitzer painted a new portrait of the Milky Way in infrared. Suddenly the veil lifted. We could see stars forming in dense, dusty nurseries, places completely dark, invisible light. We could trace the structure of the spiral arms by the glow of their embedded stars. We saw the crowded bulge at the galaxy's center, not as a faint smudge but in detail. Then came Gaia. This mission took mapping to an unimaginable scale. By measuring the positions, distances, and motions of over 1 billion stars, mainly invisible light, but with unprecedented accuracy, Gaia is building a three-dimensional dynamic atlas. It's like going from a static hand-drawn map to a living, rotating model. Gaia has confirmed our galaxy is a barred spiral. It has traced the subtle warp of the galactic disk. It's even begun to unravel the history of the Milky Way by showing us families of stars that move together, the remnants of smaller galaxies it consumed long ago. This patient, century-long effort from Leavitt's period luminosity law to Gaia's billion-star census, it gave us a blueprint of our island home. We know we live in a vast, structured pinwheel of stars, gas, and dust. And having this detailed map of our own galaxy gives us a template, a reference point. So when we look at the faint, redshifted light from the most distant galaxies, we can ask a new question. When did the first grand structures, like our own Milky Way, begin to take shape? Mapping our own galaxy was a triumph, but it raised a deeper question. How did these structures first form? To answer that, you have to look far beyond the Milky Way, and you have to look back in time to see galaxies not as they are now, but as they were. In the early 90s, an idea took shape at the Space Telescope Science Institute. The Hubble Space Telescope had just been repaired. Its vision was clear. They wondered, what if they used that new clarity not to look at something brilliant, but at a piece of sky that looked completely empty, a dark patch. No bright stars, no known galaxies. The target was a tiny area near the Big Dipper, about the size of a grain of sand held at arm's length. For 10 straight days in December of 1995, Hubble stared at that one point. It gathered every faint photon, every whisper of light. The gamble was huge. What if, after all that time, the image was just black? It wasn't black. When the data was processed, the Hubble Deep Field image appeared, and it was breathtaking. That tiny, empty patch of sky was filled, not with stars, with galaxies, thousands of them, a cosmic tapestry of faint, fuzzy blobs in every color. Some were spirals, seen edge on as thin slivers. Others were irregular clumps. Chaotic and small, each one of those smudges was an entire galaxy. And because light takes time to travel, each one was a snapshot from a different era. A different past. The most distant galaxies in that image were over 10 billion light-years away. We were seeing them as they were when the universe was only a fraction of its current age. This was more than a pretty picture. It was a core sample of the universe, like a geologist drilling deep into the earth to pull up a cylinder of rock, revealing layers of history. Hubble had drilled a narrow beam of observation deep into time and space. That one image gave a direct visual timeline of galaxy formation. It showed a clear evolution. In the early layers, the distant galaxies were smaller, bluer, more irregular. They were often colliding and merging, a chaotic building phase. As you looked at younger layers closer to us in time, the galaxies grew more structured. They settled into the majestic spirals and smooth ellipticals we know today. The ancient light in the Hubble Deep Field confirmed a critical idea. The early universe was a fertile nursery, a place of intense star birth. Those blue, clumpy galaxies were factories, churning out new stars at a rate far beyond anything in the modern cosmos. This changed our understanding. It turned cosmic evolution from a theoretical framework into an observable fact. We could now trace the growth of galaxies across billions of years, all within a single frame. The philosophical impact was just as deep. By staring long enough at what we thought was nothing, we saw nearly everything. The emptiness was an illusion. The universe is saturated with galaxies as far as our most powerful eyes can see. That single observation reshaped our sense of scale. and our place within it. It proved that to uncover the deepest secrets, you sometimes have to do the simplest thing. You just have to look and keep looking. That deep look backward was just the beginning. It set the stage for a new generation of telescopes designed to push this core sample even further into the cosmic dawn. The Hubble Deep Field showed us a slice of the universe's history, but it had a limit, a wall in time. The light from the very first galaxies had been traveling so long, the expansion of space stretched it past red into the infrared. Hubble could see some, but not enough. To see that dawn, we needed new eyes built for that stretched, ancient light. And in July of 2022, those eyes opened. The James Webb Space Telescope released its first deep field. It was pointed at a galaxy cluster, SMACS 0723. But Webb wasn't just looking at the cluster, it was using it. That cluster's gravity acted as a lens, a natural telescope. It magnified the light from galaxies far behind it, warping their faint glow into arcs and smears across the darkness. That image was a portal, a view back to when the universe was a few 100 million years old, just an infant. The light from the faintest, reddest smudges had been traveling for over 4 billion years. We were seeing galaxies just after the dawn of time, and what we saw was a shock. Theory said the first galaxies would be small, chaotic, simple building blocks starting to clump. But Webb's infrared vision showed something else. Some of these primordial galaxies looked surprisingly massive. They showed hints of structure disks, maybe even spiral arms, far earlier than anyone thought. The universe, it seemed, got organized in a hurry. This pristine light is a direct message from the cosmic dark ages. It tells a story of rapid, prolific star birth, of galaxies assembling at a breakneck pace. Our models, our timelines of cosmic evolution suddenly seemed too slow, too conservative. Webb's light is forcing a rewrite of those early chapters. The question now is urgent. What powered these early cosmic engines? How did enough gas cool and collapse so quickly after the Big Bang to forge such vast collections of stars? The answers might be in the first stars themselves, monstrous, short-lived behemoths that lived fast and died young, seeding space with heavy elements. Or maybe in the voracious appetites of early supermassive black holes, whose energy could have catalyzed star formation on a galactic scale. Every speck of infrared light in that deep field is a clue. A piece of a puzzle we're just starting to assemble. The James Webb Space Telescope isn't just showing us older objects, it's showing us a different universe than we expected. One that moved from simplicity to complexity with an astonishing, almost precocious speed. And if galaxies formed this quickly, it makes you wonder. What else was happening in that vibrant, ancient nursery? What other cosmic children were being born in that first light? That early light from infant galaxies had to come from something. It needed an engine, and in the early 60s, astronomers found it. They found the most powerful engines in the cosmos. It started with a radio signal. A point of light, star-like but blaring in radio waves. They called them quasi-stellar radio sources, quasars. When they split that light into a spectrum, it was baffling. The fingerprint of elements was there, but the whole pattern was shifted so far into the red it was almost unrecognizable. That immense redshift meant one thing. These weren't stars in our galaxy. They were fleeing, carried by the expansion of a very young, very distant universe. To appear that bright from such a distance meant their true luminosity was almost beyond comprehension. A single quasar can outshine 1,000 Milky Ways. So what could generate that much energy from a region not much larger than our solar system? The answer was a cosmic monster. A supermassive black hole, but not the quiet, dark kind, one in a state of violent feast. Imagine a whirlpool in space. At the center, gravity so strong not even light escapes. But around it, a vast disk of gas and dust spirals inward, like water circling a drain. This is the accretion disk. The material rubs together under immense pressure and friction. It heats up to millions of degrees. It glows with a fierce, white-hot light across the entire spectrum. That's the quasar, the light from a black hole's dinner table. It's the most efficient engine for turning matter into energy we know of, far outpacing nuclear fusion. By studying the spectra of this light, astronomers could do something. They could weigh the monster at the center. They measured how fast gas was whirling in the accretion disk. They used the Doppler shift in its spectral lines. From that speed and the size of the disk, they could calculate the mass needed to hold it all in orbit. The numbers were staggering, millions, even billions of times the mass of our Sun. All crushed into a tiny point. These black holes weren't just inhabitants of galaxies. They were their beating hearts, their violent youth, and the light from quasars does more. On its billion-year journey to us, that beam passes through the wilderness between galaxies. It pierces clouds of primordial hydrogen. Atoms in those clouds absorb a specific color from the quasar's light. They leave a dark line in its spectrum. Because the universe is expanding, clouds at different distances absorb the light at slightly different, shifted wavelengths. The result is a barcode, a dense thicket of hundreds of dark lines on the red side of the spectrum, the Lyman alpha forest. Each line is a snapshot. A single cloud of hydrogen at a specific moment in cosmic history. By reading this forest, astronomers can map the distribution of matter across billions of light years. They can measure the temperature and clumpiness of the early universe. It's like using a brilliant lighthouse to illuminate the fog around it, revealing every swirl and density. Quasars are more than ancient relics. They are active probes. Their intense light is now used to find other things. It can illuminate faint, diffuse gas clouds that would otherwise be invisible. It can even backlight lonely planets drifting in interstellar space. They confirm a link. Giant black holes were not late arrivals. They were there, blazing at the center from nearly the beginning. Their growth shaped the galaxies around them. Their fierce light, a signature of the cosmos's most turbulent adolescence, still guides us. It guides us to the hidden framework of all that is. Quasars showed us the monsters at the center of galaxies, but to find where life could start, we needed something much smaller, just a tiny, repeating dip in the light from a star. For so long, the only planets we knew were the ones in our own solar system. That was the whole model. That changed in the 90s. Astronomers found a new way to listen to starlight. Not for its color, but for its rhythm. They looked for a faint, regular dimming. When a planet crosses in front of its star from our view, it blocks a tiny piece of the light. Think of a gnat flying past a stadium light miles away. That's the scale, a dip of maybe 1% or even less. But if that dip comes back every few days or months on a schedule, that's the sign of an orbit. That was the transit method. This needed patience. It needed precision on a huge scale. Then came the Kepler Space Telescope. Launched in 2009, it was built to do one job. To stare without blinking at one patch of sky, a patch with over 100,000 stars. For years, it measured the brightness of each one, again and again. It built a light curve, a heartbeat graph for every star. That data was full of dips. Kepler found thousands of new planets. It showed that solar systems aren't rare. They are everywhere. Most stars have planets, and a lot of those systems don't look like ours. There were hot Jupiters, giant worlds orbiting incredibly close to their suns. There were mini Neptunes, a whole type of planet we don't have here. And crucially, it found rocky worlds in the habitable zone where temperatures could allow liquid water. But the story in the light goes beyond the dip. When a planet transits, a sliver of the star's light passes through the planet's atmosphere, if there is one. Atoms and molecules in that air absorb specific colors. So if you compare the star's light spectrum before the transit to the spectrum during the transit, you can subtract the star's own fingerprint. What's left is the fingerprint of the planet's atmosphere. This is how we've found things in the light of distant suns, water vapor, sodium, methane. Even carbon dioxide in the skies of other worlds. That faint, ancient starlight, changed by just a whisper of an atmosphere, is now our first tool, a tool to study the climate and chemistry of other planets. It moves the search for life out of just speculation. Now we look for biosignatures, certain mixes of gases like oxygen and methane together that are hard to explain without something alive. Missions like the James Webb Space Telescope are turning this into a fine art, probing the air of Earth-sized planets around small, red stars. This whole new field, comparative planetology, this census of thousands of worlds, was built on watching for a fleeting shadow in ancient light. It changed planets from just celestial ornaments into a basic part of the cosmic story, and it changes how we see things. We're not just mapping stars and galaxies anymore. We're starting to map the universe of possible homes. So next time you look up at a star, that steady glow you see might, right now, be flickering. A flicker from a distant world passing in front, sending a quiet signal across the light years. The Viking landers reached Mars in 1976. They were the first to really look for life there. They scooped soil into chambers, added nutrients, watched for signs of breathing. They got chemical activity but not clear biology. The life question stayed open, but Vikings sent back something else, a new kind of light, the first clear color pictures from the surface. A pale pink sky, rust-colored ground, boulders scattered. That visual light made Mars a place, a world you could picture yourself on. The landers also had spectrometers. They read the light reflected from the rocks. That light told a chemical story. It confirmed the rust, iron oxide everywhere. It described a thin carbon dioxide air. A cold, dry world, seemingly dead. For a while, that was the picture. A static desert. Then the orbiters came, eyes in the sky with better spectrometers. They didn't just take pictures. They mapped the whole planet's minerals by reading the infrared light. Different minerals have unique fingerprints in that light. And the fingerprints they found changed everything. They found clays. Clays need liquid water over time to form. They found sulfates, salts that are left behind when water evaporates. This spectral light painted a different history. It showed ancient Mars wasn't always dry. Water had flowed, it had pooled, it had changed the rocks, leaving these mineral ghosts behind. The light rewrote Mars from a dead relic to a world with a past of rivers, lakes, maybe an ocean, a past that could have supported life. So the question changed. Not is there life there now, but did life ever start there when it was wet? Now this light acts as a guide. When picking a landing site for a new rover, they look at these mineral maps. They look for the spectral signs of clays, of carbonates, minerals that need water and can preserve signs of life. They follow the light to the most promising pages in Mars's story. The Curiosity rover in Gale crater confirmed it, found an ancient lake bed. Perseverance in Jezero crater is at a dried-up river delta, a place where sediments and maybe signs of past life could be concentrated. Every color image from a rover, every infrared scan from orbit, it's us reading the light of a distant sun, bounced off an alien world to decode its lost history. Mars shows a planet's past is written in its rocks, and we can read that past from the light they reflect. It's a training ground, a nearby lesson in how to look for habitability and the traces it leaves. And if a world this close could have been so different, what might be waiting on the icy moons out in the dark? Mars showed us how to read a planet's history in its light. But there was one picture taken from the farthest point we've ever been that used that same reflected light to show us something else, something about us. Voyager 1 had finished its tour of the outer planets. It was headed out into interstellar space. On February 14, 1990, from 6 billion kilometers away, they told it to turn its cameras back. Toward home, it took a last set of pictures of the solar system, and in one of those frames, caught in a beam of sunlight, was Earth, not the blue marble. Not the sphere of clouds and oceans. From that distance, it was a pale blue dot, a speck of dust hanging in a sunbeam. That one pixel of light was everything. Every person who ever lived, every civilization that rose and fell, every piece of art, every discovery, every joy, every struggle, all of it in that faint speck of light. Carl Sagan pushed for them to take that picture. He thought about what it meant later. He wrote about how that dot shows our posturing, our imagined self-importance. The idea that we have some special place in the universe. It was a clear lesson, a lesson in humility, but that pale light wasn't about despair. It was about responsibility. From the edge of our home, the borders disappear. The fights that take up our lives seem small. Against all that dark, that dot is all we have. It's the only home we've ever known. The photo came back on radio waves across the solar system. It became an icon, a symbol of how unified we are and how fragile. It changed how we saw things. From citizens of countries to caretakers of one tiny world, it asked us to think as one civilization, with one shared fate on that speck. That view outward, that perspective from a robot looking back, makes you ask something. If all of life's grandeur is on that one pale dot, then what is life? What are we and everything around us made of? To answer that, you have to stop looking at the light from stars and planets. You have to look at the light that shows the molecules inside us, the story written in the vibrations of atoms. That pale blue dot and everything on it is made of recycled stardust. And that's not just a poetic idea, it's a physical fact. The proof is in microscopic grains of dust that fell from space, because not all ancient light comes as photons. Sometimes the message is locked inside matter itself, inside the most primitive meteorites, the ones left over from the solar system's birth. Scientists have found something. Tiny grains smaller than a human hair, grains of silicon carbide, diamond, graphite. But these aren't like anything on Earth. Their atomic structure, their isotopic fingerprints are alien. They're older than our sun. We call them pre-solar grains. This isn't solar system material. This is literal stardust, each microscopic speck condensed in the cool, outer atmosphere of a dying star. A red giant or an asymptotic giant branch star. Then that star's final winds or the shockwave of a supernova blasted them out into the interstellar void. They drifted for millions of years, maybe billions, and then, by chance, they were swept up in the collapsing cloud of gas and dust that would become our solar system. They survived that violent formation untouched and eventually landed here inside a meteorite. To read their story, we don't use light telescopes. We use ion probes, mass spectrometers. These instruments can analyze a single grain. They measure the ratios of different isotopes, different forms of the same element. The ratio of carbon-12 to carbon-13, or silicon-28 to silicon-29. These ratios are a nuclear signature. They're frozen records of the specific nuclear reactions happening inside their parent star when the grain formed. It's like reading the light of that star, its unique nuclear fingerprint, but preserved in atomic structure instead of a beam of photons. So what do these tiny time capsules tell us? They reveal a rich heritage. The grains didn't all come from one type of star. The isotopic signatures point to many different stellar parents. Some came from low-mass stars like our sun will become. Others bear the mark of massive stars that ended in supernova. Some even suggest origins in rare events like nova. The message is profound. Our solar system wasn't brewed from a uniform, primordial soup. It was assembled from the ashes of many different stars, from multiple generations of stellar life and death across the galaxy. We aren't just made of star stuff. We are made of specific stars' stuff, A galactic community contributed to our raw materials, so when you hold a meteorite, you're holding a piece of the early solar system. But within it, you're also holding physical pieces of ancient starlight, grains that witnessed other suns. This is the ultimate proof of cosmic recycling. The iron in your blood, the oxygen you breathe, the carbon in your DNA, their atoms were forged in stellar cores and scattered by stellar deaths, long before our own star ignited. These grains make the vast cosmos feel connected. We are walking archives of galactic history, and this tangible link to other stars makes you wonder. If starlight and stardust are the legacy of stars, what becomes of that legacy when the stars themselves finally fade? What's the ultimate fate of all this ancient light? All that ancient stardust, all those signals from across the universe, they face one final fate. They can fall into a black hole. These are places where gravity wins completely, where the escape velocity is faster than light. So by definition, nothing gets out, not even light. Yet it's right at the edge of that darkness where light does its most incredible thing. Before it vanishes, it shows us the extreme warp of reality. Just outside the event horizon, that point of no return, there's a shell of space where gravity is tuned perfectly for light itself. That's the photon sphere. The pull there is so immense that photons, particles of light, can be forced into unstable orbits. They travel around the black hole like a marble rolling perfectly around the rim of a vast bowl. If a photon in that zone is nudged slightly inward, it spirals into the abyss. Nudged outward, it escapes to infinity. It's a cosmic tightrope, the last possible path for light before it's lost. And just beyond that sphere, the bending of light becomes a powerful lens. The intense gravity warps the paths of any light coming from behind the black hole or from its own superheated disk of matter. It distorts that light into brilliant rings and arcs. This isn't an artist's idea. In 2019, the Event Horizon Telescope collaboration showed it to us. They combined data from radio telescopes across the globe to create a virtual telescope the size of Earth. Their target was the supermassive black hole at the heart of the galaxy M87. The image they made was historic. A dark central shadow, the event horizon's silhouette, surrounded by a fiery, asymmetric ring of light. That ring is the photon sphere, or light just outside it, being bent and lensed by the black hole's incredible gravity. We saw the same thing later around our own galaxy's central black hole, Sagittarius A. The light in that image is a last message. It comes from matter in the accretion disk, superheated to billions of degrees, in its final moments before it crossed the event horizon. We're seeing the last photons that struggled free, their paths twisted by the black hole's spin, carrying a precise record of the conditions at the edge of oblivion. By studying the shape and size and asymmetry of that ring of light, scientists can do something remarkable. They can weigh the black hole with precision. They can measure how fast it's spinning. They can test Einstein's theory of general relativity in the most extreme gravitational environment possible. Every detail in that warped light is a test. So far, Einstein's predictions have held, but even small deviations could point toward new physics. This light also touches on one of the deepest puzzles in theoretical physics, the information paradox. If anything that falls into a black hole is lost forever, including the information about what it was, it violates quantum mechanics. The struggle of light at the event horizon is central to that conflict. By studying the last light to escape, we're probing the boundary where our two most successful theories of reality, relativity and quantum mechanics, meet and break down. From the darkest objects in the universe, light gives us our clearest map of the severe curvature of spacetime. It shows us where the rules as we know them reach their limit. And having looked into that ultimate darkness, we have to pull our perspective back out to the very largest canvas where light reveals not a single point of collapse, but the grand architecture of all existence. Black holes are one extreme, but to see the universe at its largest scale, you listen for a different kind of echo, a fossil whisper from the very start. Not in one beam of light, but in the way everything is arranged. In the first few 100,000 years, the universe wasn't quiet. It was this roaring sea. A plasma of particles and light all coupled together. Photons pushed against protons and electrons. That created pressure, and gravity pulled everything in. That push and pull made sound waves, real waves rippling out through the soup. They're called Baryon acoustic oscillations. It's like dropping a stone in a pond. The splash is the hot, dense beginning. The ripple expanding out is the sound wave. But in this cosmic pond, the ripples had a limit. They could only travel as far as sound could go before everything changed. The change happened when the universe cooled, atoms formed, the fog lifted, the light that was trapped suddenly shot free. That's the cosmic microwave background. And at that instant, those sound waves froze. They left a permanent imprint in the matter, a faint, spherical shell of slightly denser stuff with a radius of about 500 million light-years. That shell became a preferred scale, a cosmic fingerprint. For billions of years, gravity worked on that imprint. It pulled matter toward those frozen ripples. Galaxies formed more easily along those shells. So today, if you map the universe in 3D, you don't see a random scatter of galaxies. You see a subtle tendency. Galaxies are separated by this specific scale. It's like finding every city on Earth is roughly 500 miles from another. That pattern isn't random. It's a relic. To see it, you need a map, not of one galaxy, but of millions. That's the work of projects like the Sloan Digital Sky Survey and DAISY. They don't just take pictures. They capture light from countless galaxies, get precise distances from their spectra, and plot them in a vast 3D atlas. In that sea of data, statisticians hunt for the signal. They look for that faint excess of galaxy pairs separated by that 500 million light-year scale. It's a statistical whisper. You only hear it by surveying a colossal volume of space. When they find it, they have something powerful, a standard ruler, because we know the true physical size of that frozen sound wave from the early universe, thanks to the cosmic microwave background. So when we look at a galaxy survey and measure how big that ruler appears to be at different distances, which means at different times, we can measure how much the universe has stretched in between. It gives us a direct measurement of the expansion history. And what does this fossilized sound tell us? It confirms the story from the supernova. The expansion of the universe is accelerating. The scale of those ancient sound waves appears larger in the nearby universe than our models of a coasting or slowing expansion would predict. Space has stretched more than expected, pushing galaxies farther apart on that ruler. It's another completely independent line of evidence for dark energy, a whisper from the first moments carried on the light of billions of galaxies, helping us measure the fate of everything. This echo ties the universe's loud beginning to its silent, accelerating future. It shows the largest structures we see today were seeded by the faintest tremors at the dawn of time. That fossilized sound from the cosmic dawn is a whisper from the beginning. But to understand what keeps the stars shining now, you have to look at the light from our own star. For centuries, the sun's energy was a mystery. What could burn for billions of years? The answer came in a line of color, a moment of daytime darkness. During a solar eclipse in 1868, the astronomer Pierre Janssen pointed his spectroscope at the sun's corona. In its rainbow of light, he saw a bright yellow line. It didn't match sodium, it didn't match any element known on Earth. It was something new, something only the sun could make. They named it helium, after Helios, the Greek sun god. For decades, helium was a celestial element, a signature in sunlight we couldn't find here. That was a revelation. The stars were made of things we hadn't discovered. But the deeper meaning of that line was still hidden. It was a clue waiting for its crime, and the crime was the mystery of stellar power. Physicists calculated that if the sun were made of coal, it would burn out in a few thousand years. But geology showed Earth was far older, so the sun needed a different engine, a vastly more potent one. The theory arrived in the 1920s and 30s, nuclear fusion. In the heat and pressure at a star's core, hydrogen nuclei are forced together. They fuse, and in that fusion, a tiny bit of mass becomes a vast amount of energy. Einstein's equation and the ash left over from this reaction, it's the second lightest element, helium. Suddenly, that yellow line in the solar spectrum wasn't just a curious component. It was the direct evidence, the exhaust, the proof of process. The light from our star carried the fingerprint of the nuclear furnace at its heart. Spectroscopy let us read the fuel and the byproduct. We could see the hydrogen, the raw material, and we could see the helium, the finished product. Its spectral line was a quiet testament to the fusion happening deep below. This connected everything. The chemistry in starlight wasn't passive. It was dynamic, a ledger of an ongoing reaction. The same process that makes helium in the sun's core powers every main sequence star in the sky. That simple yellow line validated our understanding of stellar life cycles. It grounded the grand theory of nuclear physics in the observable light from our own daytime star. We later found helium on Earth in natural gas deposits from radioactive decay, but its first discovery was in the light of the sun, a gift from the cosmos. A piece of a star's heart revealed in its glow. This moment tied the energy that warms our planet to the fundamental forces governing all matter. The light told us not just what stars are, but what they do. It showed us they are engines, transmuting elements, bathing the universe in the energy of creation. And if light can reveal the engine of stars, it can also reveal the shadow that may one day bring everything to an end. Helium's yellow line showed the sun's nuclear heart, but to see the heaviest elements being forged, you needed a new sense, a sense that could feel space itself shudder. Gravitational waves were a prediction on paper for a century, ripples in space-time from accelerating masses. Einstein doubted we'd ever detect them. They were too faint, the disturbances too tiny, but in September 2015, LIGO heard it, a chirp, a faint shiver, just a fraction of a second. It was two black holes, each about 30 solar masses, spiraling and merging. Over 1 billion years ago, that detection opened a new window. We weren't just astronomers anymore. We were listeners, but the true symphony started 2 years later. August 2017, LIGO and its partner Virgo felt a new tremor. This one was different. It lasted longer, almost 100 seconds. The signature pointed to something less dense than black holes. Something with more structure, 2 neutron stars, the ultra-dense cores of dead stars in a final dance. The event was named JW170817, historic on its own. But then, something unprecedented. 1.7 seconds after the gravitational wave ended, NASA Fermi telescope saw a flash, a short gamma-ray burst. From the same patch of sky, the chirp had a visual counterpart. For the first time, we felt the shudder and saw the flash of the same event. The race was on. Observatories everywhere swiveled toward the source, a galaxy called NGC 4993. What they saw in the following days was a new kind of light, a kilonova. A glow that started blue and hot, then faded to red and infrared over a week. The radioactive afterglow of material blasted out during the merger. As the neutron stars ripped apart, they sprayed out neutron-rich debris. In that extreme environment, atoms captured neutrons furiously, building elements heavier than iron. Rapid neutron capture. The light from that kilonova carried the spectral fingerprints of those new elements. It confirmed a long-held theory, the cosmic alchemy that creates about half the elements heavier than iron, gold, platinum, the uranium in Earth's crust. It happens in these violent collisions, the gold in a wedding ring, the platinum in a catalytic converter. They're souvenirs from a neutron-star merger. Billions of years before our solar system formed, this single event, JW 170,817, marked the dawn of multi-messenger astronomy. We perceived the universe with two senses. The gravitational waves told us the dynamics, the masses, the spins, the orbital dance. The light told us the aftermath, the chemistry, the energy, the ejected material. Together, they provided a complete story, one no single messenger could tell. It proved that to understand the universe's most violent chapters, we must listen to its ripples and see its light in concert. We're not just watching the cosmic movie anymore, we're feeling its soundtrack, and with every new chirp, every corresponding flash, we add another page. A rich, multidimensional page to the story of how everything came to be, including the atoms that make us. For a long time, we just saw points of light. Then we learned to split that light, to time its pulses, to measure its faintest whispers. We found that every photon is a courier. It brings news from a distant place and from a distant time. The redshift of a galaxy, the helium line in the sun, the ring of light around a black hole, these aren't just facts, they're sentences in a language the universe has been speaking since the beginning. And this long conversation shows a pattern. Our cosmic enlightenment, it doesn't come from the universe changing its message. The light from the Big Bang has been streaming past us for over 13 billion years. Supernova exploded, quasars flared, neutron stars merged, all before there was anyone here to see it. The data was always there, embedded in the fabric of reality. Our progress has been about building the translators. First, the prism to split starlight, then the photographic plate to capture it, the radio dish to hear its hiss, the space telescope to see its infrared glow, the interferometer to feel its gravitational ripple. Each new tool is a new kind of time machine. It lets us receive a part of the signal we were deaf to before. We're not inventing the story of the cosmos. We're gradually tuning our instruments to hear it being told. It's a narrative of profound humility. We are not the authors of this epic. We're its audience, sitting in the very back row, learning to listen more closely. And yet, it's also a story of incredible optimism, because it means the universe is, in principle, knowable. Its history isn't hidden. It's broadcast in all directions for all time, written in the only medium that can travel the voids between galaxies' light. The quest is endless. There will always be another layer of the message we haven't decoded. The nature of dark matter and dark energy are written in the light, in the way it bends and the distances it reveals. The potential for life on other worlds is written in the subtle dimming, the spectral fingerprints of alien air. The first seconds after the Big Bang might be written in the primordial gravitational waves we are just now learning to detect. The light is always waiting. Our task is to keep building better listeners, so when you next see a clear night sky, remember you're not just looking at space. You're looking at time. You're surrounded by an ocean of ancient messages, a cacophony of whispers from every chapter of existence. And with every new telescope we point upward, with every new frequency we learn to see, we lean in a little closer. We ask the cosmos to speak up and to tell us the next part of the story. We started with a simple question, are we alone? And we ended up with a universe that's anything but simple. There was the debate over island universes, the coordinated detection of light and gravitational waves, 20 moments that show a cosmos more dynamic and strange than we imagined. Each flicker of ancient light chipped away at our ignorance, replaced myth with measurement, replaced wonder with a deeper understanding. We saw light act as a time machine. It carries images of infant galaxies. It works as a chemical analyzer. It tells us what stars and planets are made of from across the gulf of space. It serves as a gravity probe. It reveals the invisible mass that shapes galaxies, the severe warp around black holes, and it's our ultimate cosmic historian. The entire story of expansion and acceleration is held in its wavelength. These discoveries are more than facts, they're connections. They remind us we're part of a story billions of years in the making, woven into the cosmos by the atoms in our bodies. And the story is far from over. New eyes on the sky are coming. The Vera C. Rubin Observatory begins its immense survey. Future gravitational wave detectors will listen for fainter ripples. The next chapters are waiting. What will the next beam of ancient light reveal? Maybe the nature of dark energy comes into focus. Maybe we find unambiguous signs of a living world orbiting another star. Or we detect a signal so unexpected it forces us to rewrite the book again. The universe has been broadcasting its history since the first moment. We're only just learning how to listen.